for the flange and web. Okay, so that is what we are going to deal with. Okay, so now we have a beam that is simply supported. Okay, the whenever you see questions like this, it always like bothers you, like if we draw a transformation over here, this is x, y, you have rotation about z. It always bother you, like, hey, what is this distance? Okay, so it is a known fact that is not given. I repeat again, it is a known fact, it is not given. But is it important? Okay, so I'm going to show you why it is not important. Okay, so we know, right? So if we were to sketch our free body diagram, okay, we're going to sketch our free body diagram. So we know that this is our point A, and this is our point B. And we know that exactly at the center is 180 times 10 to the power 3 Newton. And we know over here you have your AY, and we know that we have BY. But because the length is the same over, the distance is the same over here, and there's only one load, okay, with this, we can come to a conclusion that AY is equal to BY. And then we do static analysis, summation of forces in the y direction is equal to 0. So it's AY plus by BY minus by 180 times 10 to the power 3 is equal to 0. The fact that AY is equal to BY, you have 2AY is equal to 180 times 10 to the power 3. We have AY, which is equal to 90 times 10 to the power 3. And this is equal to BY also. Okay, so that part is done. So now when we draw our shear force diagram, right, when we come draw our sketch our shear force diagram, right? So this is V, this is X, and this is plus 90, this is minus 90, right? So 0, 0.5, and then this, I believe the distance is up to 1 meter. So it goes from here to here, and then it sinks down by 180. It go horizontal, then it go up by 90. So i.e., we know that they want to find at a distance NN. But unfortunately, we are not given X. But is it important? No, because it's not important because the shear force in that direction over there is equal to 90 times 10 to the power 3 Newton. Okay, so sometimes in your exam, there are information that are not given. When I don't give those information, means the information is not important. Okay, so from here we have concluded that Vmax is equal to 90 times 10 to the power 3 Newton. Okay, Vmax is equal. Now also given to us, right? IZZ is given to us as equal to 5.813 times 10 to the power of what? Times 10 to the power minus 6 meter 4. Okay, so we have these two value. So what we are going to find is we're going to find the shear stress, okay, at point A. So this is equal to Vy over Izz Qz divided by T. And Vy, we know that is what? Constant, right? So at point A or point B, you can realize this, that the Vy and the Izz are constant. Okay, don't move it. Okay, so 90 times 10 to the power 3 QZ at point A, we found QZ at point A. We're going to use our values over here. QZ at point A is equal to 80 times 10 to the power 3. Okay, so we have found that this is equal to 80 times 10 to the power minus 6, right? IZZ is equal to 5.813 times 10 to the power minus 6. Now, the thickness, okay, this is where things comes important. I'm going to get this diagram. I'm going to put it down here. Now, at point A, I'm going to draw a line across. Okay. Right? And then I'm going to sketch the shear flow. Okay, so the shear flow look like this. Again, the longer the red line means the higher the process. Right? So at point A is at the interface, it's at the junction of the flange and the what? And the web. Right? So the problem is at point A, right? What is the thickness? Right? What is the thickness we're going to, if you look at point A, it's at the intersection of the flange and the web. Do you use 160 or do you use the twice of the 20? Okay. And the answer is use the smaller thickness. If you use the bigger thickness, what will happen is this. If you use the bigger thickness, you will calculate a lower stress state. Okay. So we know that this will be equal to twice because you have left and right. The thickness will be 20 times 10 to the power minus 3. So the outcome of this will be equal to 90 power 3 times by 80 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 20 power minus 3 is equal to 30. I got 30 point. Wait, did I get? I get 30 point. Let me check. So I got 30.965 times 10 to the power 6. This is Pascal. Okay, so let me do this again. So the first moment of area, we knew it was what? It was 80, right? So over here, we knew the first moment of area. Let me check. It's 80. Yep, it's correct. 5.813. 5.813. So 90 power 3 times by 80 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 20 power minus 3 is equal to 30.965. Now, it's correct. Okay. So now, if we were going to sketch, okay, this is just a sketch. Later on, you will know why it looks like this. Okay. So if we go to sketch, the shear stress, okay, so assuming this is the centroid, right? Assuming that this is the centroid, okay? And then over here, this is our Y value. I'll change color. This is our Y value. Okay. So we know that I'm going to draw an orange line. Right? So the distribution will look like that. We know the analysis furthest away is going to be 0. So this over here, this is our shear. This will be our Y. Okay, it will look like this. It will stop here. Okay. And then because the thickness changes, you're going to see this step, right? Then from here to here, it will do this. Okay. this step over here, this horizontal line over here, this is because the thickness is equal to 0.16 meter. It shot up, okay, at the y value at this point over here, is because now the thickness over here is equal to 0.04 meters. Okay, so that is why we determine this value over here. Are we clear? Okay, this is a very important concept that you all need to know. Okay, I'm serious over here. Okay, this is a very important concept that you all need to know. Okay. Okay, so now we have determined that it's 30.965 times 10 to the power 6. Okay, so the next thing that we are going to do is we're going to find the shear stress at point B now. Okay, so again, point B is over here. Yes or no? That's our point B. So we have Vy over Izz Qz over T. So Vy, remember rule number one, V and I are constant. I.e., regardless of the position of where you're interested in, Vy over Izz always is constant. Okay, so again, you put this down as 90 times 10 to the power 3. Okay, divide by 5.813 times 10 to the power minus 6. Okay, and then your Qz at point A, which we have at point B, which we have calculated Qz at point B is equal to 60 times 10 to the power minus 6. Okay, so we will have over here 60 times 10 to the power minus 6 multiplied by twice, and this is 20 times 10 to the power minus 3. Now this one is a no-brainer because point B is at this region, is 20 millimeters thickness. Because you have left and right web, you have to do the twice. Okay, so this will be equal to 90 power 3 times the 60 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 20 power minus 3. This is equal to 23.224 times 10 to the power 6 Pascal. I'll do it again. 90 power 3 times the 60 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 20 power minus 3. Index error. 5.813 power minus 6 divided by 2 divided by 20 power minus 3. 23.224 times 10 to the power 6 Pascal. So we have determined our A and B. Okay. Now, the next part, okay, which I've done an add-on, is we are going to derive the shear stress distribution equation. So, i.e., we are going to derive the function of this curve, and we are also going to derive the function of this curve. Okay, we're going to derive the function. Okay, so I'm going to get this diagram, and we are going to derive the function. Now, deriving the function, we've done it before. Okay, we are going to apply what we have learned, okay, from this diagram. Okay, whatever we have learned from this diagram. Okay, we're going to, whatever we have learned from this diagram,